Good morning, good afternoon, and good evening. Welcome to the 28th AEC Global Teamwork virtual event. My name is Renate Fruchter, and I'm the founding director of the PBL Lab at Stanford, home of the AEC Global Teamwork and host of this annual event. For 26 years, we gathered at Stanford in May for this exciting and engaging event to listen to the global student team presentations, sharing the evolution of their project and team process, discussing with industry mentors their solutions as they unfold the project stories in our SciFi interactive iRoom. Thank you again, SciFi, for the continued support. Regardless of the COVID-19 challenges and travel restrictions, we continued our AEC Global Teamwork journey and reimagined collaboration at the intersection of people, place, process, and emerging technologies, keeping in mind that this year's student generation never met in person. But before we start to dive into the student team presentations to follow shortly, I would like to thank all our partners in our vibrant AEC Global Learning Network, faculty and industry mentors, alumni, owners and sponsors who so generously dedicated their time, attention and knowledge to all our students in order to create a close to real world project experience. Special thanks to DPR Construction, Swinnerton Builders, and HOK for their sponsorship this year. A big shout out to our industry partners who collaborated with me to define and launch this year's 3 challenges: sustainability, IPD, and technology, inviting students to develop creative approaches to address the 15th Sustainability Challenge, Equity, the 12th IPD Challenge, Buildings as Products, and the 3rd Technology Challenge, Parametric Adaptability. Another big thank you for the generous support of our PBL visionary technology sponsors that enable us to continue to develop new ways of working and learning and stay socially connected in virtual worlds during these pandemic times, integrating data, models, and disciplines, and embedding AI, VR, parametric modeling and optimization in the daily work practices of our students. I have to say, it has been a great pleasure to mentor and work with the 28 students from Stanford and 9 partner universities worldwide, representing 16 nationalities, coming from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students were distributed in 4 AEC global project teams. All the teams were tasked to collaborate and virtually design and build university buildings in challenging locations, addressing local hazards such as earthquakes, hurricanes, flooding, local code regulations, labor conditions, and tight construction sites. In preparation for the virtual event, all 4 teams prepared project evolution story video presentations that were asynchronously reviewed and assessed by 37 AEC industry mentor judges. All teams then gave a TED-style short team pitch online to discuss their solutions with the mentors. To view all team presentations, please visit our PBL AEC Project Gallery website. I hope you will be inspired. Without any further delay, River team, the floor is yours.
Good afternoon and good evening, everybody, and welcome to the pitch presentation of Team River 2021. Today we are going to present you our concept next year's spring. We This is Team River in 3 time zones from 7 countries and 7 universities. This is our owner team, distributed in 4 different countries and whose commitment we greatly appreciate and are thankful for. And now, let's introduce you to our site, which is located in Weimar, Germany, in the Goethe Park next to the River Ilm. Some site hazards are the fact that Weimar is a UNESCO World Heritage City and needs to be treated accordingly. We have wind coming from the southwest and tight intersection and access roads. However, this challenge encourages us to develop a small kit of parts with given dimension restrictions. The fact of the shallow water table was solved by using self-drilling macropiles and a waterproof concrete slab for the foundation. And by creating an earth embankment, we were able to bear the risk of flooding. Our site has a breathtaking view to the river and the park. It is quite extroverted with a good connection to the other university buildings. Our targets for the project are divided into the 3 categories: design, user experience, and construction and use. They were there from the beginning, steering our design to life cycle process. Also, we created 3 icons for our interesting challenges. These will appear in black on the bottom left of the slide, provided the challenge is addressed with the presented content. The 4 concepts from the winter quarter were evaluated in a decision-making process, with the criteria sustainability, architecture, thrill, usability, and financing. The winner was next year's Spring Sprout, to which we will introduce you now. As said, our building is located in the Goethe Park, and we were inspired by its founder Johann Wolfgang von Goethe, a Renaissance man, landscape planner, mayor of Weimar, and also a poet. And one of his past poems is Next Year's Spring, referring to something new. His verse inspired us for our design and led to our concept goals of bridging the gap between the past and the future. We connect to the past by passive measures, and we reach for the future by active measures and a sustainable process. A further approach for this connection is done by intergenerational equity. But what is intergenerational equity? It is conserving fairness and resources for future generations. Equity in general can be a difficult concept to grasp, but when we dove into the literature, we quickly fell in love with the definition of intergenerational equity. With it, we can impact all 3 pillars of sustainability: the environmental, the social, and the economical.
So now we are showing you how we approach the 3 interesting challenges. For the equity challenge, we decided to work with low CO2 impact materials, and with our green roof, we added a new layer to the park. For building as a product, we decided to develop a small kit of parts of our building elements and also introduce KPIs to measure the acceptance outcome. And for the parametric adaptability, we parameterize our building geometry, and by doing material iterations and including a green roof, we reach a DGMB Platinum. One benefit of the public-private partnership between Team River and Riverbank University is the allowance for this involvement of CMEs in teaching the next generation workforce. The involvement will be through a 10-year PBL Lab established by the university that enforces the CME's Sustainable Prefab Product Library. So before we enter the building, here we can see how our building is integrated to the site. It is orientated that we have the main benefits of diffuse sunlight, wind, and shading. And 3 large historic trees needed to be moved during construction, so this provided additional shading from the southwest. And now we know where the building is, so let's take a look inside. On the right and left, you can see interactive information touch wall, where you can receive information about accessibility for people in wheelchair. If we follow the path up the stairs, we notice that the middle part allows us a lot of light and different shading. And you can see curved load-bearing ramped oil walls from the past, which regulate the indoor climate. And if we go upway to through our fire protection glass doors to the upper student area, here more regular ramped earth walls are highlighting the gesture of framing. So this illustrates the rationale of what we see is a dynamic and internal gesture in contrast to each other. On a quick overview of our architecture floor plans, we show you how the rooms are arranged around all levels. We use the wings for student and working areas, small and large classrooms, and the northeast for the auditorium. We solve many integrational challenges together, and we are showing you a selected ones. We use rammed earth for the load-bearing internal walls and CLT for shell walls and floor panels. We move away from the using glulam for beams and columns and now use a pure softwood instead. And this material choice has a positive impact on our building global warming potential as measured by the BOM. It also emphasizes how we connect the past with the future and incorporate old knowledge experiences. And in collaboration with our architect, we decided to follow a very regular structural system, which helped us to stick to our small kit of parts. And the MIP system selection was driven by the local environment, energy efficiency, and unique properties of the building. A ground source heat pump is our primary system due to its compatibility with our site location, and rammed earth physical properties enable us to use a secondary system previously not considered. So ventilation systems are tailored to the needs and shapes of the spaces. Now we are located in the open student area in the second level, where students get a chance for informal interaction with professors. And also they are provided big and small open working areas. And this big glass facade opens up the view to the beautiful Goethe Park. We coordinated MIP and structure system by beam underpass and penetration with consideration to only penetrate in the middle 50% of the beam span and middle 50% of the beam depth to avoid shear and moment critical zones. And we want also a minimum of 40% prefabricated items, including rammed earth walls, beams, CLT floor panels, columns, ducts, and curtain wall panels. So these materials are located in a product library stored at the university. So teams hoping to adapt the building to new usage or utilize rammed earth in construction will have the resources needed. So the next generation workforce made up of student interns will fabricate the architectural rammed earth walls.
All right, and we will now continue our little tour here on the roof. And here you can see that we are using this new layer of the park, and you can get a new view of the area. And the elements here are a continuation of the inside and the shade from the strong wind from the south. As we go down quickly down the elevator here, we see these rammed earth walls again. And of course, rammed earth is great because it helps control the humidity in the building. And it also has a large thermal mass, which stabilizes the temperature, passive measure also. It also has these layers, like the layers of history, of course, referring to the past, like in the grains of wood or in rock. And we also added this 40-centimeter layer of concrete in the bottom as a water table in case of flood or other water measures. And as you can see, there are a lot of different spaces in this building, and there's a lot of different spaces for different people, which has been a priority for us. Here you can see the entrance and how the gesture leads you along. But how do we actually build these rammed earth curved walls? We want to prefab them, maybe, but in our case, that makes sense because we had a quite wet climate with the flooding, so we could not do it on site. But should we do it subcontracted or self-performed was then the next question. And through our KPIs, we found out that self-performed prefabrication performed much better. And another aspect of it was then that, okay, earth is pretty cheap, but making the formwork is not. So we want to optimize the building shape to make sure that we could reuse the mold. And here we made sure that the building was created from the same radius. So these big load-bearing walls, they have the same radius built from the same ellipse. And here you can see a little bit of a sketch on how the parametric journey was and who was involved. It was the initial architectural idea, and then we unified the radius of the ellipse. We made the elements load-bearing, it became much thicker, and then we panelized the elements so they could fit with the size restrictions. And then we adapted the openings to fit for people and span and light. And here you can see again some of the parameters and also the final size and the weight of the elements. And of course, all of this fits again in the end so that people can actually stand there and enjoy the building in the end.
Our process goes from procurement to closeout. It is centralized around the supermarket, which to us is home to the prefab packages from our SMEs and also where the rammed earth walls fabrication will take place. We then move into QA/QC for the rammed earth walls at Bauhaus University, which is central to the region. Rammed earth walls follows the same testing procedure as concrete, and that informed us about that decision. The kit of parts for the SMEs and the rammed earth blocks are transported to the job site for crane assembly. Our first stop in the process, as we mentioned, is at the SMEs. Most of our suppliers are within 20 kilometers of the job site, and we chose ones engaged in prefabrication to take care of the kit of items, including curtain walls, sky roof, CLT panels, and MEP systems. Using this and the prefab rammed earth, we are at 52% prefabrication when our goal was 40, and we're utilizing 92% of our building systems from SMEs when we were initially aiming for 70%. Moving into the supermarket, which is only 5 kilometers away from the site, we use Manufacton as our management medium. Manufacton is a program that links to the BIM models and acts as a centralized order and production tracking system. We can track the stages at which our supply chain are at with our prefab packages and also monitor our performance with the prefab rammed earth wall blocks. It color codes the components in the BIM model and links it to the mobile app so it can be utilized by on-site personnel. As you can see, we are at 0.76 as in our productivity factor, which is higher than the benchmark of 1. Using Fuser VDC, we check the peak workflow in the supermarket for any bottlenecks. As you can see, the rammed earth panels are transported by the forklift to the first truck for delivery. In the corner, we see our next generation workforce hard at work with our formwork, and then 2 more deliveries of column and beam elements to the site are in this peak workflow day. Here's a visualization of the rammed earth walls to be constructed by the next generation workforce. We were committed to using natural materials in the building, so this assembly for us is actually decomposition. Lifecycle financial management is seldom applied in construction to its full potential. Through integration with our LCFM, we were able to use multiple optimized schedules through Alice, the AI schedule optimization software, and the procurement dates from Manufacton to find the best value for money through liquidity planning. But what is liquidity planning? A liquidity plan is used to divide loans over a known period of time. When there's no liquidity plan, for us, the interest paid was almost twice as much. Comparing the top 3 optimized schedule from Alice, we found that option 1 with 2 curtain wall crews is the winner. We were able to save 21,000 euros that would have been paid with no value added.
Our next step was to look at the risks in and out of construction. Focusing on the accepted risk in construction, we gained information about their impact and their probability of occurrence by surveying methods. The 2 main accepted risks were the flooding and the next generation workforce. Their impact and probability were then divided across different work packages, and the triangle distribution was applied to them. The resulting probability and impact were then multiplied together to get the severity, which could be predicted with a Monte Carlo simulation. Here we can see that at the 90% confidence interval, the cost contingency is 5%. We also found the duration contingency for offsite to be 15 days for the rammed earth walls fabrication. And the duration contingency for the on-site construction was chosen at 22 days to account for the event of flooding. Before we take you to the on-site assembly, here is a peek at our intelligent interoperability in our design for manufacturing and assembly. In construction, we integrate Alice and Fuser to investigate scheduling and logistics, Manufacton to optimize productivity and track the supply chain. After that, we move into life cycle with liquidity planning and risk management, which informs supply chain and construction, and in turn iterates the design through visualization in Meeting VR, Miro, and Aris VR. And modeling in Rhino, Grasshopper, and most importantly Revit, which combine most of the technical software we use. Using all of these, we created our 5D green design for manufacturing and assembly. The concept of intergenerational equity exists in construction by using renewable energy through permanent on-site generators that provide power for our electricity construction equipment. At first, the site had to be excavated and backfilled. The second action that took place was the boring of micropiles and then was scheduled concrete curing and waterproofing of the slab. We can see with brown and left colors the right laydown areas and trucks arriving from the warehouse in specified times for elements delivery. Then cranes, after unloading the trucks, place the elements at the correct position. The tower crane can reach all the building's footprint, whereas the mobile crane can reach 2/3 of it. Here is also displayed the flood event, how the construction stops during flooding, and the site is secured by flooding barriers. Afterwards, the remaining actions take place for the fulfillment of the construction process.
All right, let's take a quick pause on our green roof before we discuss how our building performed against goals and targets. We tracked our green building performance against the DGNB standard. DGNB stands for
Deutsche Gesellschaft für nachhaltiges Bauen
and is the German equivalent of LEED. We achieved a platinum certification through key design changes such as the green roof, utilizing softwood structural framing, a change driven by BOM results, which we'll discuss later, and implementing a liquidity plan responsive to ALICE scheduled data, as well as green construction, which put in place pollution plans and low noise electric equipment, the way that Alex just discussed. We monitored the environmental and financial impacts of proposed design changes using the sustainable target value and target value design tools. For example, we considered switching from 3D printed concrete slab to CLT slab for design and constructability reasons. We confirmed with the STV and TBD that this change kept us within our targets. The STV helped us understand the trend of environmental impact through design, though many of our specific materials were not available for deeper analysis. To better understand the impact of these materials, we used the Buildings and Habitats Object Model, or BOM, Lifecycle Assessment Toolkit. This enabled us to understand the embodied global warming potential of our actual materials against the evolving geometry of our building. We analyzed 576 materials combinations by parameterizing live Revit geometry, utilizing the BOM to transfer it to Grasshopper, and varying material options for slab, core, interior and exterior walls, and structural framing. As providing a cost-effective building to our owners was a key goal, we evaluated the impact to the TVD before finalizing materials changes. Let's dive deeper into our TVD performance. Following the crit session, we moved away from a rough RS means estimate to the BKI cost and planner. After this, we consistently fulfilled our targets. A key update was the decision to omit the 3D printed concrete slabs and commit to self-performed prefab rammed earth as a structural and architectural component in the building. We also implemented a green roof and updated our general conditions based on our offsite process. This increased our cost a little, but with further updates, such as the removal of the photovoltaic panels, the cost dropped to 7.6 million euros. Based on the framework of our PPP contract, we estimated our annual rent. We used a rough estimate of the annual cost for maintenance and operation to set an approximate target value. As earlier discussed, the STV and TBD were continuously analyzed and ultimately impacted our final life cycle cost of 18.6 million euros.
All right, wrapping up the challenges. For the Building as a Product challenge, we want to point out our three main approaches. Using sustainable industrialization and stakeholder commitment, we were able to achieve our set KPIs with 93% small-medium enterprise utilization for regional identity, 52% prefabrication, and 62 kilograms a square meter carbon dioxide impact. Moving on to the parametric adaptability change. We used Grasshopper to panelize our rammed earth elements so we can use the same formwork for all our curved walls. To adapt to the challenge of moving up the LEED or DGNB evaluation, we assessed our material selections with the BOM tool to see what can impact have different materials. Furthermore, we created the aforementioned liquidity plan to save on interest costs with the AI created schedule. Finishing the challenges with the equity challenge. So for the equity challenge, we want to point out our three approaches. Of course, our idea to connect the past with the future within intergenerational equity. Also, the integration of the project into the regional culture and avoiding having a negative impact on the future. With that, we're using the student workers and, for example, the green roof for a more regional impact. So moving to our technology we used, we created this chart to show you what kind of softwares we used and what matters. So some softwares were used by just certain disciplines, others had impact on the whole team and were used on a regular basis. For instance, we would like to name Meet in VR here. As we never met in persona, the VR software we used pretty much every week for our meetings and our stand-up reports, and it helped us to feel a little more of connectedness. Another software we want to point out is Miro. Miro is an online sketch board or sketch wall, and it helped us really in the early stages in the project or of problems with brainstorming or problem solving. And now let's move in kind of a regular week of our lives here in the course to show you how we dealt in our planning. So we started off with Niele Visual Planner. It's an online pull planning tool. So with that, we can set deadlines or see what are our duties for the week. Our communication is mainly over Discord, but also for the meetings, as we just mentioned, Meet in VR was a big thing. Of course, now here we are all in Zoom. So for having an issue, we started off in Miro, this online sketch wall, to start sketching on ideas. Then we went into Revit to really draw these ideas onto the board. And then we pulled the data out of Revit, analyzed this over our common OneDrive folder in Excel. Again, a very important tool here to see if all the data add up and add up with the cost we set. If that all add up, we go back in our building with Iris VR to really get a feel for the building and also, of course, going for a soft clash detection. Finishing up with our team process. So as Renate mentioned in the beginning of this class today, we never met in persona, and till this day, not anyone has met. We also have this issue with the 3 time zones, as every other team has as well. But all the softwares, all this work together helped us to grow together as a team. And to prove that, we're kind of currently planning to meet in person and do a Europe summer vacation trip with the team. With that, Team River wants to thank all you for your attention, the owners, the mentors, the industry partner, and of course, Renate for all your support during this project. Thank you.